the first thing we did, we had this operation which was parameterizing lines in R2 or R3, and this was a line through the point with coordinates say x0, y0, z0 in the direction ABC can be parameterized by x of t, y of t, z of t is equal to x naught, y naught, z naught plus t times ABC. Maybe I should put these angle brackets here just as a formality. So it's x0 plus ta, y0 plus tb, z0 plus tc. And remember the picture that goes with it. It's very instructive, especially for this content. We've done very little calculus so far. Most of this is just geometry, right? So it's very useful for you to have a picture of what's going on in general. So if this is your initial point P0 and here's some velocity or some direction V, then everything on this line here can be described by your vector, which has endpoint here at the origin, and then the tip of this vector is on your line here, and that's your parameterization vector with x of t, y of t, z of t here. All right, so maybe I could also draw a red vector here. This is your initial position vector from the origin pointing to the point P0 here. So this is P0 plus t times v. Right, so this was the main, one of the main conclusions we got from last week, and this gave you a way of describing lines in 3 dimensions or 2 dimensions. And now one of our motivating questions was, all right, so we have very nice shapes that we could describe so far in 3 dimensions. We know how to describe a sphere earlier last week. We now know how to describe lines. And now, well, lines are one-dimensional flat objects in a sense in 3 dimensions. And the question now is, how do we describe planes, right? Planes are, like sheets of paper in 3 dimensions. They seem awfully simple, but we don't know how to describe them quite yet. So what we did was an operation. We introduced an operation last time called the cross product. This is an operation on vectors in 3 dimensions only. And what you see, what we saw last time was the formula for the cross product was if you had a vector that is, let's call it v, and this has components v1, v2, v3, w, it has components w1, w2, w3, then this tells you that the cross product between these, so v cross w, must be equal to the following. In the ith component, or the x component, if you will, you do v2 times w3 minus w2 times v3. And now in the y component, so if you just pretend x, y, and z goes here, labeling these columns, then in the y component, you remove, well, in a sense, you look at the entries that are not in the y column. And so you do v3, you move this column over here, and you do v3 times w1, and then you subtract off w3 and v1. And then finally, for the z component here, you remove this column and you look at this square here, do v1 times w2 and w1 times v2. So this is v1 times w2 minus w1 times v2. All right, so here's your formula for the cross product. And also, this is a quick trick, right? If you just write, if you're doing computations, if you write your vectors this way, just one on top of the other, and you write the components this way, then it saves you time setting up the cross product. But you really just look at these little squares here, and you can do your calculations of what the cross product could be. Okay, so this was a formula for the cross product. I never really explained why this is important. Right now, it just seems like some sort of contrived operation we could do. But let's say the important property is v cross w is perpendicular to both v and w. All right, so the picture is this. It turns out that if you have a vector v here, I'm going to draw that, and you have another vector w. Remember that when we look at the dot product, it was nice to see that if I could find a vector that's perpendicular to a single vector just by solving the fact that I want my new vector dotted one of my original vectors to be equal to 0, right? And then we had some choice in what that vector was, up to scaling and direction. But in this case, if you imagine W and V as lying along a sheet of paper, then I want to describe a direction that is normal to them both. That is not just perpendicular to one of V or W, but to them, to both V and W, because that gets me a direction of up off the sheet of paper. And this gives us a method of doing so. The resulting vector might look something like this. The scaling is completely off. I apologize. But this is the picture here is if I have some sort of plane where V and W live, then this vector here is perpendicular to both of these. So it's perpendicular to the plane itself. And you could take this as a fact. It comes by a rather long computation, but it's one of those, once again, just comes down to trig and a lot of algebra. But you get the fact that V cross W is a vector that's perpendicular to both of these. And you also get the fact that you have a funny formula for what V cross W is. You have the fact that the magnitude of V cross W is equal to the magnitude of V times the magnitude of W times sine of the angle between them. So, okay, so this gets us a vector that's perpendicular to both of these vectors here. And what happens when sine theta is 0? Let me address a few questions in chat. There's kind of a non-rigorous way of seeing which way V cross W points geometrically. It's called the right-hand rule. It tells you that if, let's say I have my blue vector here and green vector here, if I were in physics, I would say, okay, well, I would point if I want to figure out which direction V cross W is, because there's two perpendicular directions, right? There's one direction this way and there's one direction this way. Then I move my hand so that if I have my open hand like this, I point my fingers along along V first, and then I curl my fingers in the direction that W makes with V. So in this case, W is opening up in this direction. If I drew W here, I'll be opening up the opposite direction. So if I take my right hand, I need to curl my finger in the way W is oriented with respect to V. And in this case, my thumb points upwards. So this is, where my thumb points is the orientation of the cross product. All right, so there's always a unique vector that the cross product is. You do have the fun property that W cross V is minus V cross W. All right, other properties that you could check for yourself is V cross W is equal to minus W cross V. They're both perpendicular, but one's going to be the opposite direction. You also have the fact that for a constant C times V cross W is the same thing as CV cross W, which is the same thing as V cross C times W. Okay, so you could scale each of these vectors first and then take the cross product. It doesn't really matter which one you scale, and you get the same result. Whereas the geometric interpretation of the cross product is 0. So the cross product is 0, then this is 0, which means that if you are non-zero vectors, right? If neither of these vectors are 0 and your cross product is 0, then that means that sine theta is 0. So that means that W is collinear with V. That means that W is pointing the same direction as V up to a sine, right? So that's what this tells you. And now you could also interpret this in kind of a separate fashion. This formula here you could recognize as the following. It's the fact that if you have a vector V here, and I'm going to draw W here, then what you could do is I could sort of make a parallelogram formed by these vectors. This has angle theta. And so we know that W, the length of W, so the length of this side times sine of this angle here, that's sort of straighten this thing out. W sine theta times V, the length of V here, gets you the area of this parallelogram. All right, so that's one other geometric interpretation of what these represent. Not very satisfying. This is I presented something out of the blue, and I claim there are all these magic things that that this satisfies. You'll have to trust me on this, or read the textbook, or go through the proof yourself. It's a rather long calculation, but using the fact that this is what V cross W is, and you could evaluate its magnitude, you end up by applying laws of sines and cosines on triangles. You get these properties. Okay, so these are just fun properties that these satisfy, but they're not the main use of what we care about quite yet. So let me do a comparison between dot and cross products All right, so the first thing is to note that one of these works in any dimension and the other doesn't. So here's a dot product, here's a cross product, and the first thing is it takes in, well, let me try and do a table here. So it takes in, they both take in vectors, so that's good. Valid dimensions are as follows: any dimensions, but the cross product only 3. All right, you can only input vectors that are 3-dimensional. Its output is a number for the dot product, or a scalar, in other words, and the cross product gets you another vector. All right, so these are big differences between the dot and cross product. So these are a brief comparison. There's a lot of other things that are different. One of these is, if you look at this property here, v dot w is the same thing as w dot v, whereas v cross w is minus w cross v, for example. There's a minus sign that happens when you switch the order. There are a lot of examples of these differing, but these are some of the main ones I've listed here. So when do you use this? Let me get to that right now. Cross product, like I said, is used to actually construct a vector that's mutually perpendicular to two given vectors. So main use of cross product for us, describing planes. All right, so here's the main use of cross product. Let's draw a picture. So let me draw a picture of a plane. Right, so this is a plane P in 3 dimensions. And now let's say the plane contains a point. I'll call it little p here. It has components x, or as coordinates x naught z, y naught z naught. Now, what distinguishes any other point on the plane? So let's say I have another point here. All right, so let's say p0 is what I just drew, and this is another point p. So how do I decide if p is contained in the plane p? Now, so one thing I could do is as follows. If I already have my plane here, I can find a vector. Okay, visually speaking, I'm not saying mathematically speaking. Visually speaking, I could find a vector that tells me which direction up is. All right, if I have a flat sheet of paper, I could tell you, I could indicate with a pen or pencil or whatever which direction up is. Up means that it's vertically, in a sense, away from the plane, and it makes right angles with the plane. I'm going to draw that here. So everywhere on the plane, there's going to be a vector, right, that I'm going to call n with some fixed components, a, b, and c, that is telling me which direction up is. So if I now have an arrow that points from p0 to my turquoise point p here, so here's my orange arrow from p0 to p, so I'll call this arrow p0p. What angle does that make with the direction up that I have? Supposing p is also on the plane, and this is my direction up, my normal vector n. What's the angle? Is the angle less than 90 degrees, equal to 90 degrees, or greater than 90 degrees? Right, so this is exactly 90 degrees. So if n is normal to p, normal just means orthogonal, and p is in my plane p, then the vector p0p is orthogonal to n as well. This is going to be orthogonal here to n. Okay, so what does this tell me? This tells me, so I haven't used a cross product yet, but we'll get there. It tells me that if I know this crucial bit of information, which is what this vertical direction is, n, then I can actually describe pretty well, knowing that, if I describe my point, my plane, by a point that it does contain for sure, which is x naught, y naught, z naught, and I tell you a direction that up is with respect to this plane, then I can give you an actual algebraic equation with a plane. And here's how you do it. Let's say p has coordinates x, y, z. So the equation of the plane is, in this case, so p is in the plane. So p is in the plane if and only if it satisfies your vector n. So here I'm not using the cross product, I'm using the dot product. N dotted with the point p, the vector p0, p is equal to 0. Now let's write this out. This means that if my coordinates of this vector n are the components are a, b, and c, and I want to dot with p0p, what's the x component of p0p? So this is the arrow that has tail at p0 here and the tip at x, y, z. So what's the component in x? Let's say, what's the x component of this arrow? Right, so it's x minus x naught, right? You want to subtract, it's this point. If you make each one of these, p0 and p themselves arrows with tails here, then it's this arrow minus this arrow. So it's this arrow here, and it has x minus x naught components, and the x component in the x direction, then y minus y naught, then z minus z naught. this must be equal to 0. So this means that you could expand this out. This is a x minus x naught plus y, or sorry, plus b, y minus y naught plus c, z minus z naught is equal to 0. Or you could also expand. This becomes, so if I group everything here and then I look at just, these are constants now, right? A times x naught, b times minus y naught, c times minus z naught, and I move everything to the other side. Then I could write this as d, where d is equal to following. Then you get the equation of this plane. This is the equation of the plane P that contains the point P0 with normal vector n. All right, any questions on the equation of a plane so far? We'll get to cross product soon. I know, I said we're going to use cross product. We've used a dot product here, but we'll get there. Okay, so where does the cross product come in? Well, it turns out that in a lot of the cases, the moral of the story so far is if I know n and I know a point that the plane contains, then I can very easily write down what the equation of this plane is. Now, there's a couple issues with this, which is it's very hard to know the normal n in the first place, right? If you think of, if I describe to you what a plane is, the plane that I want, naturally your first instinct isn't say, okay, I'm going to get your normal vector n and a point that I want my plane to contain, and here's my plane. Usually you give information on points, say, right? You'd say, okay, if I have 3 points, if I have three, I want to have 3 points, in space, and I want to join all these 3 points in a single plane, let's say. And then you want to figure out, what exactly the equation of that plane is. Well, in that case, you don't have a normal vector n. You need to create your own normal vector n. Or you could say, okay, I have a point and I also have a line in 3-dimensional space. And I want to have a plane that goes through both the plane and this line. And that's also hard to do because, whereas a normal vector n, you don't have one. You can also make variants of that, right? Let's say I have a plane, a line, and also a point that's off the line, and I want to find a plane that, contains the point and is parallel to this line, or I just want to find a plane that goes through a line that does not contain the point. Then what do I do? So there's a lot of work that would go into actually creating planes because giving a normal vector n directly often isn't the case. You got to find n. So cross products are used to find n, which is difficult part. So the difficult part is to find the normal vector, and this is where cross products are used. And so let me try and do some examples. Find the equation of a plane containing the following. Containing the points, let's call this P0, P1, and P2. All right, so I'm not going to actually plot this out, but I will draw schematically what these points are. All right, so I have P0, P1, and P2. Okay, and now visually speaking, I want to find a plane that contains all of these. So a mystery plane. The issue here is I don't know what normal vector I have. Right? I'm given 3 points that lie on this plane. I have no idea what the normal vector is, but is there a way for me to create one? So certainly I know that if I have my displacement vector, my vector pointing from P0 to P1, any normal vector this direction, right? Any normal vector to the plane is also going to be normal to this vector. And furthermore, if I have another vector here from P0 to P2, that normal vector is also going to be normal to this direction here. It's going to be perpendicular here. And in fact, if I draw it this way, what should the normal vector be, right? So I could use a cross product, as Raphael suggests. I could take the vector this, cross with that, and that gets me an artificially constructed unit vector here. So the strategy is construct our normal vector. So does someone want to get me the components of P0, P1 first? So P0, P1 is the arrow from P0, 0, 3, 4 to P1, which is 1, 2, 0. Right, so I could subtract, it's 1 minus 0, 2 minus 3, 0 minus 4. So it's going to be 1 minus 1 minus 4. And okay, similar method. Remember, so a crucial thing that you want to know, you want to do here is you want to, when you're valuing the cross product here, these arrows must be based at the same point. I mean, if you recall to what the cross product was doing, it's basically taking you want to make sure that, you standardize P0 here. So you value P0, P1, and then P0 to P2. So you want to do, as a systematic thing, it's easier to do it this way. So now you have P0 to P2, have -1 minus 0, and then 6 minus 3, which is 3, and then 4 minus 4, which is 0. And so you get the components for this vector here, which is -1, 3, 0. And now I want to take the cross product. So does someone want to give me the x component of this cross product here? Okay, so we have -12, and the reason for that is to look at s component, you do this times that, which is 0, minus this times that, which is -12, but you got to do minus again on the -12, so actually +12, it looks like. Right, so every time you multiply in this direction, you got to multiply by -1, right? So this is 0 minus -12, so that's +12. And then what is the y component in this case? The y component here, you move this column over here, do this minus that. This should be -4 times -1, which is 4, minus 0. It's fine. And then you have this, which is the z component is 1 times 3 minus -1 times -1, right? So that's 3 minus 1, 2. So our normal vector here has components 12, 4, and 2. Okay, so that's great. We could now do the following. We have a normal vector, and we could choose any base point we want. For simplicity's sake, just for the visual demonstration, let's just choose P0 as well here. Okay. In essence, I could choose any of these 3 points, right? There are 3 points on the plane, so I could express any other point that I want to be on the plane just by drawing an arrow from that point to any of these 3 points that I know for sure are on the plane to get my displacement. I'm just going to choose P0, and what I get is the dot product of this and the displacement has to equal 0, which means 12 times x minus x naught, which is 0, because at P0, that's the coordinate, x naught equals 0, plus 4 times y minus 3 plus 2 times z minus 4 is equal to 0. And if you want to clean it up a bit, so one thing to note here is, well, I'll say this a bit after. You could clean this up a bit, to simplify things. And you could do 12x plus 4y plus 2z is equal to what you have left over. You have -12 here that you move over here, and you have a -8 here that you move over here. So that's going to be equal to 20. And you could simplify this all again, right? This is 6x plus 2y plus z is equal to 10. All right. Now let me point out a couple things. We've done a few manipulations here to get from this. So in a sense, this is really the true, geometric meaning of what a plane is, right? It's very straightforward to see what's happening here. You have a normal vector whose coefficients or whose components are 12, 4, and 2. You could have just divided out by 2 in this case on both sides because of 0 here, and you could have gotten 6, 2, and 1 already. But regardless, you know a direction of the normal vector just by reading the coefficients of this. And this is telling you the dot product of a displacement vector where you have a base point 0, 3, minus 0, 3, and 4. And your displacement is given by this, and this dotted together is equal to 0. All right, so geometrically, this makes a lot of sense for what a plane has to be. You could simplify all this to get a very nice, a more nice algebraic expression here. But even in spite of all this simplification, all you've really lost was information of where the base point was. You got to recover this. 0, 3, and 4 still solve this equation because it's on the plane, but it's less obvious where these went. However, you could still look at the coefficients of this here and immediately read off what the normal vector is, right? It's 6, 2, 1. Or scale this by 2, both sides, you get 12, 4, and 2 just from the coefficients here. All right, so the important point here is if you see an equation of a plane like this or put it in a form like this, the coefficient in front of the x is the x component of the normal vector. The coefficient in front of the y is the y component of the normal vector, and the coefficient of z is the z component of the normal vector. It's very easy to see directly. Which of the following planes are parallel to the plane above? Let's just use the same plane that we had. So let's do one that's 2x plus 2y plus z is equal to 1. And also, let's say minus 3x minus y minus 1/2 z is equal to 300. right? So these are two planes here. And so what's the strategy here? It's to read off exactly what the normal vectors are here. Okay, so one thing is, you'll often see, in plane, when it comes to planes, you get a lot of these equations floating around, but really everything you need to know from planes are encoded in the normal vectors that are associated with them. All right, so just look at the coefficients to get the normal vectors. So for A, the normal vector is 2, 2, 1, and B, the normal vector is -3, -1, -1 half. And what you see is 2, 2, 1 isn't really a multiple of 6, 2, 1, right? So how do you see this? Well, if it were a multiple, then each of these components must scale correctly, because you see that, for example, for this, 2 is, a third of 6, right? In other words, 2 times 3 must be equal to 6. And now if I want 2, 2, 1 to be completely a scalar multiple of 6, 2, 1, then I need to scale this by 3 as well. Well, if I scale this by 3, I get 6, and this is certainly not 2. So I can't scale 2, 2, 1 to become 6, 2, 1. All right, this is not a multiple of 6, 2, 1. And whereas in this case, that for B, this is equal to, well, -1 half of 6, 2, and 1, right? Move the -1 half inside. You can check it component-wise. Divide 6 by -1 half, you get -3. 2 by -1 half, you get -1, and so forth. So this means that B is parallel. Geometrically, what does this mean? Well, if you have two sheets of paper that never intersect, right, that they're parallel with each other, then certainly if I look at their normal directions, their normal vectors must also be parallel to each other. Okay, so the statement of whether a plane is parallel to a plane is equivalent to whether their normal vectors are parallel to each other. Okay, and so we see that. Maybe I'll draw a picture here. Let's say this was my original plane. Did I label it? I guess I didn't. Maybe it has a plane. This is 6, 2, 1, and my plane in B is something like this. All right. Actually, I think I got the order reversed, but the normal vector here is this plane B. It's a bit shorter than the previous one, but you can see that these are, if you drag one vector into the other, you're going to see that they line up exactly, which means that they're parallel to each other, so their planes are parallel. Now, how do I know B is not the same plane as the one before? There's a bonus question, I guess. I don't ask this, but I certainly know that B is, by looking at the normal vectors, it's parallel to my plane here. How do I know it's not exactly the same thing as the plane up there? Right, I know the constant's different, right? I know that this, if it were the same plane up here, then I would have to divide this by -1/2 as well, right? This would be -5. But because these are not algebraically the same equation, their solutions are going to be different. So this is not exactly the same thing. All right, so note that 300 is not equal to -1/2 times 10, right? Which is the right-hand side of this. So B is not the same plane as previous, just a translation of it. All right, so let's try and do a different variant of this, which is the following. So what angle does the plane A make with our original plane, which was 6x plus 2y plus z is equal to 10? Right, so the strategy here is to find the angle between the normal vectors, right? If you have two intersecting, so first of all, the first observation is, if I'm in 4-dimensional space and I have these 2-dimensional objects, right? Two planes, they're both 2-dimensional. They're either parallel, or if they're non-parallel, they must intersect somewhere. In a sense, it's like if you are in 2 dimensions, right? When I have two lines, two 1-dimensional objects in 2 ambient dimensions, then these lines are either parallel or they have to intersect somewhere, right? Because I'm out of dimensions to escape, in a sense. In 3 dimensions, I now have two objects. Right, I have two objects. Each of the objects are 2-dimensional, 2 dimensions themselves. You can make some heuristic argument that the sum of the dimension in a sense is 4 dimensions, but that's not correct. But it helps in thinking that way, because you realize that if you're trapped in 3 ambient dimensions, you have these two objects that are 2-dimensional. If they're not parallel, then they have to intersect somewhere. And so it makes sense to ask for the angle of intersection. All right. So if I have my plane here and let's say another plane here, then I could ask for the angle of intersection here, which is none other than, if I just take, maybe I should specify, I I think I saw this in Piazza, by the way. Your textbook always asks for the angle to be the acute angle between the planes. So, it's this angle here, not this angle here. I'm sorry if Webosine was confusing. I can't, it's sort of, I can't really modify the questions like that. But in your textbook, it does say the angle they want is always the acute angle. I don't make this distinction. If I ask for an angle, you give me any angle and I'm happy. But in general, acute angle's a very nice one to visually look at. So if you take two normal vectors, let's say here and here, then right, just by some old-fashioned trig, you know that the angle between the normal vectors is the same thing as the angle here, right? So instead of looking for some weird geometric method of finding the angle between two-dimensional surfaces, you could just look at the angle between vectors, which we know how to do. All right, so the strategy here is to find the angle between the normal vectors. Okay, so how do I find the angle between the two normal vectors, or between any two vectors? What's the strategy here? So if I label this, then I have the fact that cosine of theta must be equal to the dot product divided by the magnitudes. Theoretically speaking, by the way, you could also use the cross product for this, right? If you're insane, but I mean, it works out, right? You have the magnitude this times the sine of the theta is the magnitude of the cross product, but of course, the cross product itself is such a pain to compute that no one in their right mind would try and do that. So this is to find the angle between normal vectors. You always use the dot product because it's the easiest one. The dot product is so much simpler to compute with. So n1 is, well, I guess I didn't label what these things are. Let's just call it the original, the one in gray. That's 621. N2 is going to be equal to 221. So what's n1 dot n2, anyone? Okay, so I got 12, 4, 1. Well, 12 plus 4 plus 1. Right, so remember the dot product has to be a scalar, so 17. And now we need to find the magnitudes, right? So the magnitude of this, well, so first of all, here's a useful fact or computation or just a trick to know. If I want the magnitude squared, right, that's for n1, for example, that's 6 squared plus 2 squared plus 1 squared. But another way of writing this is really just the dot product with itself. All right, so that's just n1 dotted n1. That's just a useful. Sometimes it's helpful with computations, but in this case, it's just going to be 6 squared. That's 36 plus 4 plus 1, 41, and 2 squared is, let's say that's 4 plus 4 plus 1, right, 9. So this means that theta, our cosine of 17 over, so root 9 is 3 and root 41 is God knows what. So there you go. So that's your exact answer here. Note that this angle doesn't automatically give you the acute angle, right? Because, for example, I don't know how these normal vectors are oriented. Another valid normal for this gray plane would be the downward pointing one in our orientation. And the angle between that and this would be some non-acute angle and some obtuse angle here. So depending on which normal you happen to have, you might get the obtuse angle, or you might get the acute angle. To get the other one, just subtract off 180 degrees, right? I mean, you do 180 minus whatever you had. But in this case, I'm not too particular with whether I want an acute or obtuse angle. Your textbook differs, so be aware of that. All right, let's kind of do another variant on these equations for planes. I'll let you do this one from scratch, hopefully. Let's say find the equation of a plane parallel to the plane 5x minus 3y plus 2z is equal to 6, containing the point 2, 1, and 1. So the easiest way to do this is, one, observe, find the normal. Well, the normal in this case, you want your plane to be parallel, so it has to have the same normal, right? Or at least a scalar multiple of the same normal, but why not just take the exact same normal vector? So that's 5 minus 3, 2. Now, there are two ways of doing this now. The second way, there are two methods for the second step. The first step is the direct method. The option one is to do everything from scratch, right? So you know that you have a point that you definitively want to be on your plane, and you know what your normal vector is. So you just start from scratch, and you just do 5 times x minus 2 minus 3 y minus 1 plus 2 z minus 1 is equal to 0, and then you simplify, right? But there's also a different method, which is your plane equation has to be of the following form, because you have a normal vector 5 minus 3, 2, it has to be 5x minus 3y plus 2 z is equal to some d, right? Some constant d. And you also, know that the point 211 must satisfy this equation because it has to lie on your plane, right? So if this is your equation for some as of yet unknown constant d, 211 must satisfy it. So this means that your constant is 5 times x minus 3 times 1 plus 2 times 1, right? So that's 9. So your equation here is 5x minus 3y plus 2z is equal to 9. So you could think of this as the algebraic method getting it, very direct, very nice. This is probably, geometrically more meaningful as to what's happening, but it's the same result. So now let's try our hand at a slightly different example. Let's find the equation of the plane orthogonal to the following line. All right, so the line is given to you by 4 plus t, y is equal to 1 minus 2t, and z is equal to 8t, and containing, so find the equation of the plane orthogonal to this line such that, this is your line L, such that L crosses the plane at time equals minus 1. So visually speaking, I have some line L here. I need to find a plane. It has to cross at this point here at time equals minus 1. All right, so what's a potential normal vector to this line? Or a normal vector to this plane, rather. So really important information for this line, for our purposes, is the direction, which is 1 minus 2, 8. All right, so we're going to take our normal vector to be the direction of travel of this line. So take normal to be equal to 1 minus 2, 8. And what point do I want to be on my line here? So this is P0. What point do I want to be on my plane? Right, so I want it such that the line crosses my plane at time t is equal to minus 1. So where is time t equals minus 1? Well, I'll just plug this thing in. So if I plug at time t equals minus 1, I have the point 4 minus 1, which is 3, 1 minus 2, which is also 3, and then I have minus 8, correct? And then now I can find the equation of the line, right? So I can once again try out the following. I could just do a quick way, which is have the coefficient in front. So it's 1 times x minus 2y plus 8z must be equal to, well, the following. If I want this point to be on my line, then it must satisfy when I plug this in, 3 minus 2 times 3, which is, that's 3 minus 6, that's minus 3 minus, 64, huh? So this must be equal to minus 3, is that right? Well, that's unfortunate. Okay, so that's x minus 2y plus 8z is equal to minus 67. Okay, well, at least one other person has the same answer as me, so hopefully this works out. Okay, so this is a plane that is orthogonal to this given line. Now, here's a question, and I'm going to leave this for maybe something next time that we'll start next time with. Consider the same line as above, and now the question is, how can I find the plane parallel to this line and containing the point 212? So here's a visual situation of this. I have now a line. So I have a line here, L, the same as before. I have a point here, and I want to find a plane that is, well, it's a pretty horrible drawing. I don't know how to draw this, but hopefully you get the point. I want it such that it's parallel, so this line never intersects my plane. This is quite a step up in complexity from the previous examples, and I think I'll continue this at the start of next class.